practiced simplifying radical expressions, now we're going to look at operations such as addition, subtraction, multiplication, and division with the radical expressions. So we're going to start off today with a multiplication problem. Now, adhering to our rules for radicals and our properties that we have previously learned, we can, if our indexes are the same, then we can multiply inside the radicals themselves. So I'm going to leave that 5 to the outside, and then I'm going to go ahead and put everything, since they're both cube roots, under the same radical. So that would give me 100 times 10, and that gives me a squared times a. So separately, you can see that there's no perfect cubes. But when I work out the inside, now I have 1,000, which 3 zeros will show me that's a perfect cube, and a cubed. So now I can go ahead and separate the pieces. I have the cube root of 1,000 and the cube root of a cubed. When I complete that work, this is going to create a 10, the cube root of 1,000, and the cube root of a cubed is going to be a. So I have 5 times 10 times a, or simply 50a. Now, since that came out of a cube root, I don't have to worry about absolute values. So I am completely simplified at 50a. We're going to go ahead and try another one of these. So I have 3 times 2. You can see I'm going to do my outsides because these are both cube roots. I'm allowed to do that. 3 times 2 is 6, and then inside of the cube root, I'm going to have 16 times 4. Now, I already know that that 16 is 2 4s, so I can actually write it like that, times a third 4, and then again, I have some a's I can combine. So that gives me the cube root. Instead of multiplying it out this time, you can see that I'm writing it as the factors of its lowest base, which would be 4. And then I have a cubed. Now I can go ahead and cube root. The cube root of 4 cubed is going to be 4, and the cube root of a cubed will be a. So this will simplify to be 24a. Again, because I started with a cube root, I do not need absolute values around my value. So I got my n. I actually lost my n because all of my radicals canceled out. I don't have any more radicals, so I am done with this problem, and it meets all the simplified rules. Now, we have not done any addition and subtraction. All of our problems that we've had so far had a little bit of multiplication and a little bit of division when we had to rationalize. But I want you to remember that sum and differences, you can only add or subtract if you have like radical expressions. So what are like radical expressions? So if I have 6 plus the square root of 2 plus the square root of 3, nothing there is alike because they all have different radicals. The 6 doesn't have a radical. This is the square root of 2, and this is the square root of 3. So if that were the case, that is the simplest I could get that expression. Now, if I come over here and I have 5 square roots of 2 plus 7 square roots of 2 plus 9, now you can see that I have like radicals here. I have square roots of 2. So I go ahead and add their coefficients together. So the 5 plus 7 would give me 12 square roots of 2, and then I would have that plus 9 because it would not be able to be added without the square root of 2. So I can only add them if they are the same exact radical. Now remember, there's no rule or property that allows me to add underneath radicals. So I have to adhere to them being the same radical. All right, so let's look at this problem here. At first glance, it looks like there's nothing that I can do because it appears that all 3 of these radicals are different. The square root of 45, the square root of 80, and the square root of 20. So what I'm going to do first is I'm going to use my rules and make sure there are no square roots that I can pull out. So if I break down 45, now I know that 45 breaks down to 9 and 5, where 9 is a perfect square. So I'm going to go ahead and break that guy down. 80. So 80, I have a lot of choices. I have 8 and 10, which is not really a perfect square. I have 20 and 4. 4 is a perfect square, but there's also another perfect square in 20. So I'm going to kind of keep breaking that down until I find some perfect squares in there. If I continue to do that, I can break that down into 16 and 5. So again, if you need to come over here and do a factor tree of 8, you can absolutely do that. And what I can see here is that I have all of these 2's that are going to be able to square root. So 2 times 2 times 2 times 2 is 16, and that is a perfect square times 5. And that's where I got those factors. Okay, so if you need to do that tree, just come over to the side and do your tree to get your perfect squares. So now I have the square root of 20, and I'm going to break that down into 4 and 5. Again, looking for these perfect squares. So I can pull the square root of 9 and make that 3. So I have the 3 on the outside, the 3 that pulls out, times the square root of 5. Minus 5, I can pull out the 16, comes out as a 4. And then plus 4 times, I can pull out the square root of 4 and make that 2 times the square root of 5. Now, quick multiplication of what's on the outside. I have 9 square roots of 5 minus 20 square roots of 5 plus 8 square roots of 5. So if you can see here, 9 minus 20 is going to give me negative 11, plus 8 is going to simplify to be negative 3 square roots of 5. Now notice that I could not add or subtract until I got all of these radicals to be the same. And if they don't all simplify to be the same, then just go ahead and add the like terms. So this gives me negative 3 square roots of 5. All right, so let's look at some multiplications problems, some more. So this is when I'm multiplying more than one term. So if you see here, I have a binomial almost here. I have 2 square roots of 3 plus 3 square roots of 5 times the quantity of 3 minus the square root of 3. I kind of treat those radicals like they are variables. So when I have to multiply 2 binomials, I would have to FOIL. So I'm going to do the same here. So I'm going to take 2 square roots of 3 times 3, and that will give me 6 square roots of 3. My outsides give me 2 square roots of 3 times the square root of 3. So technically that's 2 square roots of 9. I'll come back and simplify that later. Then I'll do my insides. So that gives me 9 square roots of 5. And I'll do my lasts, which give me negative 3 square roots of 5 times 3 is 15. Remember, I'm allowed to add or multiply and divide as long as my radicals have the same index. Okay, so 6 square roots of 3, nothing can be simplified here. The square root of 9 can turn to a 3, so this becomes negative 2 times 3, or negative 6. The square root of 5 has no square roots in it. If I think about 15 real quick, I get a 3 and a 5 with no square roots. So the square root of 15 will also not simplify. So when I get down to this process, I see I have 6 square roots of 3 minus 6 plus 9 square roots of 5 minus 3 square roots of 15. And since none of my radicals are the same, after I've simplified all of them, then I am done. This is my most simplified version of my expression. Okay, now let's see what I have here. I have 4 square roots of 2 plus 7, and I have 4 square roots of 2 minus 7, and I'm multiplying. So I'm going to go through the FOIL process. Now notice that these 2 binomials here are opposites of one another. So I'm going to look to see what happens when I FOIL. So I'm going to take my first together. That gives me 16 square roots of 4. I'm going to do my outsides, which give me negative 28 square roots of 2, My insides give me positive 28 square roots of 2. And my lasts give me negative 49. All right, so let's see what I can simplify. So I can definitely simplify the square root of 4. That's going to be 2. That's going to give me 32. Look at what I have from my outsides and my insides. My middle two terms become opposite, and my last is a negative 49. So when I simplify that out, I have 32 minus 49. That is simply negative 17. Now what you see here, this is actually a special case. And if you remember when we factored differences of squares, and I know this doesn't look like that, but when I factored differences of squares, they factored into x plus 3 and x minus 3. So when I multiplied that out, I lost those middle terms. That's what's happening here. These can also be called a special name called conjugates. We talked about that earlier in the year when we investigated imaginary numbers, which imaginary numbers are just simply radicals of negative 1. So these two values are conjugates, just like these two are conjugates. They're opposites one another. Now, why I'm emphasizing that is because when I have to divide by a 4 minus the square root of 3 or a 4 plus the square root of 3, to get that square root of 3 out of the denominator and perform the division, I have to use a process called conjugation. Now again, we did this earlier in the year. So earlier in the year, we might have had a complex number like 5 divided by 3 plus I. So to get that imaginary number out of the denominator, I know it's been a while, we would multiply the top and the bottom by the denominator's conjugate. And when we did that, that got rid of our imaginary number in our denominator. We're going to do the same process if it's a square root. What I'm going to do is I'm going to multiply the top and the bottom by the conjugate of the denominator. So since this is 4 minus the square root of 3, then the conjugate is 4 plus the square root of 3. So in yesterday's lesson, we talked about rationalizing. So this is a form of rationalizing when I have more than one term. So when I have 2 terms in my denominator, I use the conjugate to rationalize. So you can see that since I did the same to the top that I did to the bottom, it's simply multiplying by 1. So I'm going to FOIL out the top, and it's really not changing the value, it's just changing its appearance. So FOILing out the top, I get 8 when I do firsts, plus 2 square roots of 3 when I do outsides, 4 square roots of 3 when I do insides, and when I do lasts, I get the square root of 9. I'm going to FOIL out the denominator. Firsts give me 16. Outsides give me 4 square roots of 3. Insides give me negative 4 square roots of 3. And lasts give me this negative square root of 9. Now I'm going to go ahead and simplify. So this guy is going to become a plus 3. This guy is going to become a minus 3. Now I can combine these two terms here and combine this 8 and 3. So that 8 and 3 become 11. 2 square roots of 3 plus 4 square roots of 3 give me 6 square roots of 3, all divided by. Now here my outsides and insides are going to cancel. So I'm simply going to have 16 minus 3 or 13. So this is our simplified version. Now you can leave it like that, or you can divide both sides by 13. Either way, that is the division when I have a real number without a radical and a radical in my denominator. I use conjugation. Okay, so now is the part of the lesson like I did yesterday. I want you to pause the video, try the problem, and then come back to me and see how you did. All right, so I'm going to break these apart. I'm going to make that 75 25 times 3. I'm going to make that 48. I can factor that guy down into 16 times 3. And there's nothing I can do with that 3. So now I'll simplify and make this 3 times 5 times the square root of 3. Negative 2 times 4 times the square root of 3 plus the square root of 3. So I'll multiply my outside values together, and once I have like radicals, I'll go ahead and add those together. So 15 minus 8 gives me 7 plus 1, which should be an unknown 1 there, is going to give me 8 square roots of 3. All right, let's move on. Go ahead and pause and try these two problems and then check back for the solutions. So I'm going to go ahead and FOIL here. That gives me 10 square roots of 5 minus 2 square roots of 35 plus 20 square roots of 6 minus 4 square roots of 42. All right, so let me look at that. Square root of 5, nothing's going to come out of. If I factor 35, that goes down into 5 and 7, no perfect squares. 6 goes into 3 and 2, no perfect squares. Let me look at 21. 21 I can factor into 6 and 7, 3 and 2. Again, no perfect squares. So there is nothing that I can simplify here. So that is going to be my simplified expression. All right, let's look. It looks like I have a pair of conjugates here. So this one is going to have a lot of simplification. So I'm going to go ahead and multiply this through. So I have 3 square roots of 5 times 3 square roots of 5, which gives me 9 square roots of 25. My outsides give me 6 square roots of 5. My insides give me negative 6 square roots of 5. So you can see that canceling. We can kind of do that right now happening. And that negative 2 times positive 2 is negative 4. All right, I have one more perfect square in there. So I have 9 times 5 is 45 minus 4 is 41. So that one simplified down a whole lot. So sometimes they leave you with 4 terms. Sometimes they will simplify to just be 1 term. All right, let's look at the last one I want to do with you together, and this is a division problem. So because it's division, I need the conjugate of the denominator. So if this is a minus, I need a plus. If this is a plus, I need a minus. In this problem, it is a negative, so I'm going to multiply it by the opposite or the conjugate of the denominator, which would be 2 plus the square root of 5 on top of 2 plus the square root of 5. So let's FOIL the top. So the top will give me 6 for the firsts. The outsides are 3 square roots of 5. The insides are 2 square roots of 5. And the lasts are the square root of 25. The denominator gives me 4. The outsides give me 2 square roots of 5. The insides give me negative 2 square roots of 5. And the last are negative square root of 25. All right, so is there anything I can simplify? Well, this definitely becomes a 5. And I can add these together and these. So that gives me 11 plus 5 square roots of 5 divided by, my outsides and insides are going to cancel. This is going to become a negative 5, so I have 4 minus 5 or negative 1. Now I can divide both of those terms simply by negative 1, so let's watch what happens when I do that. I have here 11 divided by negative 1 is negative 11, and 5 square roots of 5 divided by negative 1 is negative 5 square roots of 5. So you can see that we've kind of lost the division altogether in that problem, making that much simpler. All right, I'm going to put an assignment on Google Classroom. I hope you all have a great day. Check back if you have any questions.